Welcome to Catalyst Made Up, where we ignite understanding and make learning easier. In our today's class, we'll be looking at the chemistry of alkene. I've already made a video on the chemistry of alkenes. So today, we'll be looking at the chemistry of alkene. What are alkenes? The alkenes, they are also known as olefins, and they are more reactive than alkanes because they are unsaturated. They have carbon-to-carbon double bond. We said alkenes, they are also called olefin, and they are unsaturated organic compounds because they have carbon-to-carbon double bond. Again, the alkenes, they are sp2 hybridized. And we should also know that the alkenes have one sigma bond and one pi bond. Their general molecular formula is CnH2n. N here is the number of carbon. We should also know that they are more reactive than alkanes. So these are the things to take note of when discussing the chemistry of alkenes. Now moving on to the preparation of alkenes. There are various methods in which an alkene can be prepared. One, there is dehydration of alcohol. Two, there is dehydrohalogenation of alkyl halide. 3, Kolbe electrolysis of dicarboxylic acid. 4, there is reduction of alkynes. 5, there is from cracking. Alkenes can be prepared by dehalogenation. Dehalogenation of vicinal dihalide. So these are the common methods in which an alkyne can be prepared. Let's talk on them one after the other. First one here, we say that by dehydration of alcohol. The general reaction pattern of preparation of alkene by dehydrating alcohol. Dehydration of alcohol simply means removal of water from alcohol, and its pattern of reaction is if you are having ROH in the presence of concentrated H2SO4, you will be having alkenes. So dehydration of alcohol is the removal of the alcohol in the presence of concentrated H2SO4, which will serve as a dehydrating agent, thereby lead to the preparation of an alkene. For example, if we have propanol, in the presence of concentrated H2SO4, then H2SO4 will remove water from this propanol. Then we'll be having, after removing water, we'll remove this water like this, then thereby creating another double bond between the carbon number 1 and carbon number 2. So we'll be having a double bond between carbon number 1 and carbon number 2, and the double bond is characteristic of an alkene. So by removing water from an alcohol, we've already prepared an alkene. From propanol, we are having propene. Now you can prepare alkene by dehydration of alkanol. Now we also know that in this dehydration reaction, you can be having two major products depending on the location of the OH in the compound or in the reactant. For example, if you are having you're having butane 2-ol, if you're having butane 2-ol and you dehydrate it, you can be having two different types of the product. You can be having the major product as well as the minor product. That is what the Senzel rule is talking about, that in the preparation of an alkane using elimination reaction, the two main products that you'll be having are the major product and the minor product. The major product is the product that have fewer number of hydrogen, whereby the minor product is the one with higher number of hydrogen. Now let's look at this reaction here. This is butane 2-ol. If you dehydrate it in the presence of concentrated H2SO4, now we can form water by two means. We can form water forward like this, or we can form water backward. Now if we form water forward, we are introducing double bond between this first carbon and the second carbon. But if we dehydrate or we remove water backward, we are introducing double bond between the second carbon and the third carbon. So now the two major products we'll be having is, if you are dehydrating forward, we'll be having butane. But if you are dehydrating backward, we'll be having but2-ene. So these are the two main products you will be having if you are dehydrating an alcohol. It's either you dehydrate forward or you dehydrate backward. Between these two carbon atoms, you will count the number of the hydrogen that are present there. The one with higher number of the hydrogen is your minor product, and the one with lower number of hydrogen is the major product. The double bond occurs between this carbon and this carbon. Now let's saturate this carbon. This one remain 1 hydrogen, while this one remain 2 hydrogen. Now coming back to this second one, this one remain 1 hydrogen, while this one remain 1 hydrogen. Now if you count the number of the hydrogen, this is 1, 2, 3, and the second one has 1, 2. The one with lower number of hydrogen is our major product, while the one with higher number of hydrogen is our minor product. Count the number of the hydrogen that surround the two carbons bearing the double bonds. That is how you will know your major and minor product. Another example again is, let's look at this compound here. Now, dehydrating this compound here, we can be having two products. We can be having major and minor products. In the presence of concentrated H2SO4, it's either we remove water towards our left or we remove water towards our right. If you remove water towards your right, you'll be introducing double bond between this carbon and this one. While if you remove water towards your left, you'll be introducing double bond between this carbon and the carbon here. So the two main products that we'll be having are as our product A, the second product will be so this one will serve as our second product. So between this one, the product A and product B, which one will serve as our major and which one will serve our minor? We'll count the hydrogen bond that attached to the carbons with double bond. For this first product here, this is the carbon here, this is another carbon here. Now let's make each carbon to have 4 bonds, since that is the maximum bond that each carbon can carry. The first carbon here need 1 hydrogen more to have 4 bonds attached to it, while by this second carbon here does not need any hydrogen again because all it has been surrounded by 4 bonds already. Then the second product here, the double bond is between this carbon here and the carbon here. Now let's attach hydrogen for them so that each of the carbon will be having 4 bonds. For this first carbon here need 1 hydrogen, while by the second one here we need 1 hydrogen. I will say that the one with higher number of hydrogen is our minor product, while by the one with lower number of hydrogen is our major product. So from here, our compound A here is our major product because it has only 1 hydrogen, whereby the compound B here is our minor product because it has 2 hydrogen. Those with higher hydrogen, they are the minor product, whereby those with fewer hydrogen are the major product. So this is how you can prepare alkane from dehydration of alcohol. Next one is dehydrohalogenation of alkyl halide. Alkyl halide, they are also the same thing as alloalkanes. The pattern of the reaction is your alkyl halide, in the presence of strong alcoholic potash such as C2H5OH potassium hydroxide, will be having an alkene. Now, dehydrohalogenation simply means removal of hydrogen halide from an alkyl halide. Dehydrohalogenation, removal of hydrogen and halogen from an alkyl halide to produce alkene. We can see that the majority of the process for the preparation of alkene is an elimination reaction. So, for example, if you are having chloropropane, is an alkyl halide. In the presence of strong alcoholic potash, we will remove hydrogen and chlorine to form hydrochloric, thereby introducing double bond to the alkyl halide. So from here, we will be having propene. So removal of hydrogen halide from an alkyl halide will produce alkene. Another example is you can be having something like this. Then in the presence of C2H5OH potassium hydroxide, we will now be having, we will remove hydrochloric acid. This one too depends on how you remove it. You can remove hydrochloric acid upward or remove hydrochloric acid downward, depending on how you want to remove it. You'll be having cyclopentene, or if you remove it downward, you'll be having cyclopentene. Here we will not have either major or minor product, since there is no any substance that is attached to the starting point. So this is how you can prepare alkene from dehydrohalogenation of alkyl halide. Remember the reaction condition: strong alcoholic potash. Next one is Kolbe electrolysis of dicarboxylic acid. Kolbe electrolysis of dicarboxylic acid. Dicarboxylic acid simply means a compound with 2 carboxylic functional group. Common example is the succinic acid. Succinic acid is the same thing as butane 1,4-dioic acid. So it's something like this. So this is succinic acid. It is the same thing as butane 1,4-dioic acid. Now, if this succinic acid undergo electrolysis, it will produce an alkene, majorly ethane plus carbon dioxide plus hydrogen ion. So from here, this succinic acid undergo electrolysis. It will produce ethane plus 2 carbon dioxide and hydrogen atom. Now, this functional group here, they will be the one that will form the carbon dioxide. Other hydrogen that remain will now form the hydrogen ions. The next one is reduction of alkyne. Reduction simply means addition of hydrogen to an alkyne. So if you had hydrogen, if you had a molecule of an hydrogen to an alkyne, we will be getting alkanes. Having alkyne plus hydrogen molecule, we'll be having an alkene. For example, if having butane plus hydrogen molecule, we'll now be having butane. Remember, anywhere you break one bond, you add 2 hydrogen to the point. So adding 2 hydrogen to this compound here will break one bond, making it to be double bond, which will now give us the alkane that we are preparing. So reduction of alkyne simply means addition of hydrogen to the alkyne to produce an alkene. Further reduction of an alkyne will produce alkanes. That is one of the preparation of alkanes as well. So the next one here is cracking. Cracking simply means breaking down of larger hydrocarbons into the smaller ones. We should know that an alkane can only be prepared during cracking if the cracking process occurs in the absence of an hydrogen. Because in the presence of an hydrogen, all the products of a cracking will be alkanes throughout. While in the absence of an hydrogen, the product will be the mixture of alkanes and alkenes. So an alkene can only be prepared from cracking in the absence of hydrogen. The last one we are having here is the halogenation of vicinal dihalide. The halogenation simply means removal of halogen from a vicinal dihalide. A vicinal halide or a vicinal compound is a compound that has 2 halogens attached to the adjacent carbons. They are having 2 halogens attached to the adjacent carbon. That is a vicinal dihalide compound. Example: this compound here is a vicinal dihalide because the halogen here, which is our X, attached to the adjacent carbon atoms. So removal of the halogen from this compound will produce alkene. In the presence of zinc dust, vicinal dihalide, if it is being dehalogenated, it will produce alkene. For example, this is a typical example of vicinal dihalide. In the presence of zinc dust, we are removing halogens, both halogen, and we say that anywhere you remove 2 atoms, you introduce a bond, which will now give us ethane. This is how the halogenation of vicinal dihalide take place. In the presence of the zinc dust, alkenes are being prepared from vicinal dihalide by removal of both the halogen that is attached to the adjacent carbon atoms.